Okay, we're going to do one more example here of Taylor series stuff, but there is a definition that I want to write out here. So if f can be differentiated, however you spell that, differentiated to infinity, then we can define this. So this we're going to label as p sub n, supposed to be a lowercase n there, of x. And all p sub n is going to be the n terms of the Taylor series. So it's going to have that constant f of a out in front plus the derivative f of a times x minus a plus the second derivative at a divided by 2 factorial x minus a squared plus, and then it goes all the way up to the nth term here, f to the n, f of the nth derivative divided by n factorial x minus a to the n. So the p sub n is the Taylor series, but just the first n terms. This does not go to infinity. And this is called the Taylor polynomial of order n. Just know that a lot of times on the homeworks and then eventually the test questions is that they're not going to ask you to find the entire Taylor series. They're just going to ask you to find the nth polynomial for the Taylor series. So I'll call the Taylor polynomial. So let's look at a quick example of that. Find the Taylor series and the Taylor polynomial generated by let's do f of x is equal to e to the x. This one shouldn't be too bad. And we're going to do this at x equals 0. So really we're finding the Maclaurin series here, just that special case of the Taylor series. So to do this, remember, I'm going to copy down the definition again for Taylor series. Sorry for the weird scrolling. But here is just the formula for Taylor series. To plug stuff into this formula, first we have to find the nth or the kth derivative. If our function is just e to the x, if I were to take the derivative the first time, of course that would just stay e to the x. In fact, if I were to go all the way to the nth derivative or the kth derivative, it is still at just e to the x. Remember that we're plugging in 0 into this, so plugging in 0 as our center into these values, e to the 0 is just 1. The first derivative at 0 is still just e to the 0, which is just 1. In fact, the nth derivative is still just e to the 0, which is just 1. So we're going to have 1, 1, 1, 1, 1, 1, 1 as our coefficients for our Taylor series here. So now we can go ahead and write out our Taylor series. Let's do k's this time, since we're really supposed to be doing k's. All right, so the sum as k goes from 0 to infinity, our numerators here are 1s all the way down, divided by that k factorial. That times, it's going to be x minus a, which is really just x minus 0 to the kth power. So that's it. This is the Taylor series for e to the x. It's a fairly simple one. It's actually really nice and kind of cool. Just to put that on top, this is how most people write it out. Not like that. So we're going to have that x to the k just divided by k factorial. And if you wanted to write out a few of the terms here, this as a sum is what we call the Taylor series. If I wanted to write out the Taylor polynomial, I'll do it on the next line down. The Taylor polynomial, so we would plug in 0, which is going to be x to the 0 divided by 0 factorial, which is just 1, plus plugging in 1 into this is going to be x to the 1 divided by 1 factorial, which is x. Plugging 2 into this, I get x squared divided by 2 factorial, which is 2. X cubed divided by 3 factorial, which is 6. Maybe one more here, x to the 4th divided by 4 factorial, which is 24. Now remember that this is the Taylor polynomial, so we're not going out to infinity, we're just going out to n. So this would be our nth term here, x to the n divided by n factorial. This is what we would label our Taylor polynomial of degree n. So Taylor series is the infinite series that goes to infinity. Taylor polynomial is just the first n terms of that series. Okay, I do want to show you one more example here, but it's a little bit complicated, so I'm going to pull up the book. I think I had it pulled up already somewhere. Oh, no, it goofed on me. Hold on, let me pause and I'll pull it up. Okay, we're back. I pulled up the example I want to do here. So find the Taylor series and the Taylor polynomials generated by f of x is equal to cosine x at x equals 0. So just before we jump into this question, just how amazing this is, we're taking a trigonometric function here, which you can't actually write out what this thing is, right? Cosine is just a placeholder for this process of the adjacent over the hypotenuse, where you can think of it as the horizontal point on the outside of a unit circle as it goes around. But we're taking something that's indescribable as a polynomial function, and we're writing it as a polynomial. So very powerful and very cool. Okay, so we're doing it at x equals 0, the same thing as before. And remember, to do that, we're using our formula for Taylor series, which means we have to find those derivatives going all the way to k. The reason I didn't want to write this one out is because when you take the derivative of cosine over and over again, you bounce back and forth between cosines and sines. So just kind of going through it here, f of x is cosine x. That's just our first function. If I take the derivative once, I get negative sine x. Take the derivative again, I get negative cosine. Derivative again, positive sine, and so on and so forth. So it bounces back and forth between cosine and sine, and it also alternates positive, negative, over here, negative, positive. So if I have an even derivative, which is what this 2 to the n, 2n is representing. So this is the 2nth derivative. This is just telling us that it's even. If I have an even derivative, it's a cosine. And if the even derivative is even itself, it's negative, otherwise positive. Same thing's going over here with sine. So my odd derivatives, which is 2n plus 1, is always going to have a sign in it, and it also alternates positive, negative. Remember that we're plugging in our centering point 0 into these things. So just substituting in cosine of 0 into my even derivatives. Cosine of 0 is just 1. So these are going to alternate positive 1, negative 1, positive 1, negative 1 forever and ever and ever. If I plug 0 into any of my odd derivatives, which has a sign, sine of 0 is just 0. So it's kind of looking like my even derivatives are going to have an actual value, but my odd derivatives are always going to be 0. And that's going to come out to be true. So here we have our Taylor series just kind of written out as all of the terms. So here, remember, you're plugging in just the coefficient f of 0, and then the first derivative at 0 times x minus 0 to the 1, which is just x, and so on and so forth. So what the book does is they just substitute in these values that they got up top here. So notice that f of 0, that was just a positive 1, but my second term, which has the first derivative, which is an odd derivative, is going to multiply out to be 0. Here, the next even derivative, x squared, is actually negative. And then x squared divided by 2 factorial would be that term. My third derivative is going to have a 0. Even derivative is going to have a number, and so on and so forth. All right, so just kind of writing all this out, this is going to be my Taylor polynomial here. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and this is just a little generic form of that. The book also has this nice little graph here of graphing out the different Taylor polynomials. So if you only do p of 0, you're just going to get that straight line at 1. And then p2, p4, p8, p12, all the way down. And notice that the further you take out the Taylor polynomial, the better your Taylor polynomial matches the actual graph of cosine. So cosine is that blue line there. If I go all the way to the second polynomial, it's only correct up to about the value 1, and then it diverges from it. If I go to the 4th, it's correct almost to 2, and then it diverges. If I go all the way to the 14th polynomial, it looks like it's correct all the way to about there, at about 6 or so, and then it diverges away from the actual function cosine. So what we're doing, right, is we're taking cosine x and we're generating it into its own Taylor polynomial here. And this goes back to that graph I showed you back in section 7 of the further you take out the series, the better it approximates the function itself.